So for this exam, we begin with our predict the products questions. Part A, we have sulfuric acid with heat. That's a sulfonylation reaction when we're dealing with electrophilic aromatic substitution. And given the starting substituent, the methoxy group is an electron donating group, which makes it an ortho para director. Now, given that it's not a very large group, it's probably not going to cause a great deal of bias or steric hindrance toward either the ortho or para position. And so it's most likely, in a case like this, that we would see a mixture of both the ortho and para substitution. In part B, we have the reaction of an ester with a base. This we may recognize as a Claisen condensation, where the enolate formed from one of the esters will do a nucleophilic acyl substitution onto the other ester. Part C is an alkylation reaction. Because this reaction is using LDA, which is a strong base, generally irreversible, as well as low temperature, minus 78 degrees Celsius, that tells us we're dealing with kinetic conditions, where we'll form the less substituted enolate, which is at the end carbon. The electrophile will add there, which is the methyl iodide. Part D, PCC, is an oxidation of alcohols to aldehydes and ketones. The alcohol up at the top is a secondary alcohol. It can be oxidized to the ketone. On the left side, we form an aldehyde from the primary alcohol. And then the phenol group, which is directly on the aromatic ring. There's no hydrogens adjacent to the alcohol, therefore it can't be oxidized, and that one remains unchanged. Part E is a cuprate addition. So we recall that carbon nucleophiles basically always add 1,2 to aromatic rings, and that's because they're bad leaving groups. And so if we want a carbon nucleophile to add 1,4, we need to use a special reagent such as a cuprate. The group that's adding here is the phenyl ring, and it will add in a 1,4 fashion. Part F is the reaction of a diene with an alkene. We know that that's a Diels-Alder reaction. So we get our 6-membered ring. With the double bond. And then because those two nitro groups are trans in the starting material, they will end up trans to each other in the product. Part G is an aldol condensation, and a pretty basic aldol condensation because the molecule on the left, benzaldehyde, has no enolizable hydrogens, so therefore it cannot be the enolate, it cannot be the nucleophile. That makes acetone the nucleophile, which gives us our aldol product. Part H is just a Fischer esterification. We have the carboxylic acid plus an alcohol with an acid catalyst, and so we'll form an ester from bringing those two together. Part I is an SN2 reaction. So the leaving group bromine will be replaced by iodine. Part J, we have what looks like a Williamson ether synthesis. But the Williamson ether synthesis is an SN2 reaction. Our electrophile, the alkyl halide here, is tertiary, we know that tertiary leaving groups don't work for SN2, and so this ether synthesis will not work. Now, alternatively, as an answer here, you could also say that the sodium hydride is strong enough to deprotonate the phenol, and then once you add the phenol to tert-butyl bromide, since it can't act as a nucleophile, it could certainly act as a base and trigger an elimination reaction. So ultimately, what we would expect to see in this reaction is that the desired reaction, the Williamson ether synthesis, will not work, but in fact it can do an alternate reaction, which is elimination. The next part is just a nitrile hydrolysis. This can be done under acidic conditions as it is here, or it can also be done under basic conditions. Regardless, it converts the nitrile to a carboxylic acid. And then the final part of this question, we start by deprotonating the nitrogen. The nitrogen will then do an SN2 attack onto the alkyl halide. But with an excess of sodium hydroxide, that's able to do a hydrolysis on the amides as well, so it will result in cleaving both amides. And ultimately, the product that we're interested in is the primary amine that's synthesized by this reaction.